for the introduction. So also thanks the organizers for having me in this nice weekend workshop. It's my great pleasure to give a talk here. So I'm actually going to summarize some progress in the 4-dimensional simple mapping class groups. There's technically no results from 2021, so I apologize for that if you have heard about this results before. Okay, but I did include several questions to think about, or maybe to discuss in the informal session. Okay, that's new. All right, so firstly, we mentioned some flexibility in yesterday's talk, like check use talks of simple manifolds. So for simple manifold, we mean a smooth manifold with a closed non-degenerate two form. Okay, the first theorem we learned in simple geometry or simple topology is always a double theorem, meaning that for any simple manifold, we are able to find a double chart locally at every point. It has a neighborhood that's a standard R2N. So, well, that's a formal statement, but I think locally trivial is a nice description of this flexibility here. If we look at the transition maps of the R2Ns, that's a simple morphism, meaning that we have a diffeomorphism preserving this omega 0. Okay, and in mechanics, this is a kind of nice map called a canonical transformation. And in mathematics, if we take the collection of the group of such simple morphisms, we have the simple morphism group. It is also a intensively studied object. Another aspect of the flexibility is this symmetry group in the simple category is large. By large, we mean it is infinite dimensional. Okay, if we give it the C-infinity topology, then we have a Fresher Lie group. And this kind of object is in general complicated. But on the other hand, the theorem of Milnor saying that this big group has a homotopy type of a C-double complex. So it's at least still understandable, okay, topologically. All right, so it's worth remark that in contrast to Riemannian geometry, where the symmetry groups are finite dimensional. So here we do have a large flexibility. Okay, so I think the important thing in simple geometry is it is also rich of rigidity. The first thing in rigidity side of simple topology is the symplectic embedding problems, like this detailed described in Kevin's talk yesterday. Okay, so here we have a ball, we have a cylinder, and where Kevin gave us a nice description. So you can notice that the notation I'm using here is slightly different from Kevin's notation. So in the expert notation, we have B2N pi R square, right? So here I only have B2N R. That's the same object. Meanwhile, that means I am by no means an expert in simple embedding problems. So, okay, we are wondering when do we have an embedding from the B2N lowercase r to the cylinder capital R, preserving this omega 0 induced from the R2N. Okay, so the non-squeezing theorem tells us that it's only possible if the cylinder is wider than the ball, okay? Well, actually, Arnold summarized this as a simple camel cannot pass through the eyes of a needle. So here, the point I want to make is simple sizes does matter, so they are important. Later, this kind of idea will show up. Okay. Also, it's quite remarkable that if when you try to talk up to some applied mathematician, that's my experience. When I bring up this connection to uncertainty principle, then they are very excited. They are more excited than just hearing the statement of non-squeezing theorem itself. Okay, so there are many kind of nice introduction to this connection. Like if you look at some papers of Portorich on quantization or some special theory of Maris the Gaussian, I think. They have a nice physics background, which I will not mention here, but the mathematics is quite simple. So we are trying to project a small ball whose radius is related to this reduced Planck constant h bar. And then we try to project it down to one on the phase plane. So here, if you have some knowledge of classical mechanics, this PI stands for position, QI stands for momentum. And then we are in particular interested in measuring momentum and position in one direction. Okay, this is one plane. That amounts to projecting to this B2 of this cylinder part, a B2 part of the cylinder. Okay, then you have a variance of the position and the variance of the momentum product being pi capital R squared, which is greater than pi lowercase r squared, and that's related to the Planck constant. Okay, that's the mathematics. Okay, all right. So again, the idea we want to have from the symplectic embedding problems is that the symplectic sizes are important. Okay, so in this talk, instead, I'm going to focus on another kind of rigidity phenomenon, which is the mapping class group. Okay, so I think the initial question was also brought up by Arno. So he in particular wonders if symplectic maps behave more rigid than smooth or continuous maps under deformation. So here I give the detailed definition of isotopy and mapping class groups. The idea is pretty simple, actually. We take an automorphism in any category denoted by alt m. And then we pick up two maps. If we are able to connect those two maps using a path that completely lies in this automorphism group, then we say this is the isotopy of the two maps. Okay, now we are going to mod this automorphism group by the path kinetic component, and then we get the pi 0, which is also a group. We call it a mapping class group. Okay, so we can ask the mapping class group in various categories like continuous, smooth, volume preserving, and symplectic categories. Well, there are two kinds of questions we can ask. Number one is, of course, explicit computation, right? Number two is like, how do we compare those mapping class groups in various categories? So in dimension 2, this is a very important object. Actually, I think one of the key objects in the field, geometric group theory. That's easier if we ask about the comparison kind of problem. Here I'm saying that the MCGs are the same in dimension 2. That's not precise. I think the precise statement is if you have volume preserving or symplectic, then you extend the group by V2, like orientation reversing maps. Then you get the mapping class group of the smooth or continuous category if you are dealing with an orientable object in dimension 2. Okay, but roughly speaking, mapping class groups are the same. Okay, in various categories in dimension 2. So Arno in particular is interested in the symplectic world and higher dimension, okay, dimension greater than 2. So he wonders if this symplectic mapping class group is different from the smooth or like a homeomorphic, well, topological mapping class groups. Okay. Let's say a more detailed statement of Arnold's question. Okay, higher dimensional M2n omega. Which side is the shape of sim and diff 0? So here we are restricting ourselves in the identity component of a diff. Okay, on the left-hand side, this is a 2D picture. So if we look at the diff 0 of the 2D manifold, then we only see one component of sim, which is the blue region. Okay, so here I'm drawing the infinite dimensional groups in 2D. So this big disk, black disk is a diff, and then the blue object is a sim. Okay, while on the right-hand side, we are able to find many kinetic components of sim. That's an interesting case. So Arnold's seeking for the right-hand side picture. Okay, we hope to see some of these guys in dimension 4 or higher. Actually, the first, well, I think the first theorem in this right-hand side picture is given by Paul Seidel in his thesis. Okay, so any questions so far? So that's a key question we are going to study today. All right, so we always start with dimension 2 objects. Okay, that's nice and easy, at least in some circumstances. We have those three surfaces, a sphere T2 and genus G surface. Of course, we can have more genus by attaching more handles. And we are able to indole the symplectic form, which is basically the area form locally is dx dy. Well, one way to think about this picture is we are actually classifying this Riemann surface according to their Collier dimension. So this guy, Collier dimension negative infinity, this guy, Collier dimension 0, and this guy 1. Okay. I think later in the questions, I might bring up some questions related to that. All right, but anyway, we are able to do some really simple surgeries to obtain non-compact ones by adding some punctures, like or removing some closed disks. So here I have a very simple example, like we puncture the torus ones. Okay, so we want to think about the mapping class group of the compact object and the non-compact object. Okay, the first theorem is due to Smale. We have a theorem on S2. Normally, things are easier for the spheres in dimension 2, unless you are thinking about some displacement or non-displaceable Lagrangians, just as you talked about yesterday. Okay, but yeah, for us, S2 is an easier case. Okay, so here the diff plus means orientation preserving diff. As we mentioned, we are not allowed to reverse orientation. Then those two guys are actually homotopy equivalent. And more surprisingly, this infinite dimensional group is homotopy equivalent to a finite dimensional group, which is a rotation group or Riemannian isometry group, if you think about that on S2. Okay, so that's a very strong result. We know the full homotopy type. Later, Als and Eels actually reproved Smale's theorem and generalized it to the puncture case using Teichmüller theory. I'm only stating a partial result of theirs here. So they actually proved that the full symplectomorphism group of n's puncture S2 is homotopy equivalent to the break group, like n-strand break group, provided the n is greater or equal to 4. I mean, when n is smaller than 4, we have no braiding, all right? But the homotopy type is still computable. It's like some circle or product of circles. Okay, so here, that's the animation of the break group. We have the arting generator on the left-hand side. So let's imagine this vertical disk is a sphere. Okay, so here I have 5 punctures. And then the Artin generator just swap the adjacent punctures. Okay, so that after the swapping, set-wise, we are preserving the punctures. Then we can imagine we are doing some composition of these Artin generators to make braids. We can actually make arbitrary complicated braids. Of course, we have to model some equivalence relations like the braid relation. But even after modeling that, we still have an infinite group. So this puncture sphere do have a really large mapping class group. Okay, so another actually understanding of this braid group is that it is the fundamental group of the configuration space. So this kind of understanding will actually, we have a question, I think. Oh. So something's wrong with my audio. So is it okay now?
Yeah, it's okay now. There was a little bit of noise before,
Okay,
but now
great,
it's
thanks.
okay.
All right, thanks. All right, so yeah, later in dimension 4, we are going to use this pi1 configuration space kind of interpretation of the braid group. Okay. So let's try to go to higher dimensions. The first thing is Gromov theorem on CP2. CP2 we can think it as simply connected compact four manifold, simply four manifold. Okay, that's a natural generalization of S2 if you think S2 as a CP1. Okay, then Gromov proved that it's quite parallel to Smale theorem. CP2 with the Fubini study form. The symplectic group has a weak homotopy type of PU3, where PU3 is a Kähler isometry group, which is parallel to the SO3, like Riemannian isometry here. So his proof uses pseudo-holomorphic curve technique. That's actually the fundamental paper in 885. Okay. Then we also try to find some parallel construction to punctures. This is not precise, but I would like to take this one as analog of punctures in dimension 2. Okay, the reason is the following. When we do blowups, we are going to remove simple balls. Like we have a M4 here. Of course, this construction works in any dimension, but here we restrict ourselves on dimension 4. Okay, so firstly, we have a bunch of simple embedded balls, like B1, B2, B3. And then now we do care about size because whenever we do embedding in the simple category, size does matter. Okay, then we try to do this blow up. The first thing we do is to remove the balls. This is like making punctures. Okay, we look at the complement. But we don't want to end up with non-compact guys. We want to close the boundary up. So where we have the boundary equal S3. And then we have a natural Hall fibration here. And then we are going to collapse the circle fibers. So now after the collapsing step, we are going to still have the complement of the balls. But the boundary of the balls are now exceptional spheres. Let's say those are E1, E2, E3. Okay. topologically, this blow-up construction is like connecting the original manifold with a reverse-oriented CP2s. And then symplectically, we are going to have a blow-up form whose cohomology class is given by such formula, like the original form minus the sizes times the Poincare dual of the exceptional classes. So here I'm abusing notation, like identifying the homology with cohomology, but I think this notation makes sense, right? Okay, so now I will take these blow-ups as punctured S2s in 4 dimensions. Okay, that's a rational simplified form manifolds. All right, now let's think about these mapping class group problems for these guys. So in particular, we have a collection of problems on this mapping class groups or symplectic isotopy problems. Those problems are taken from the textbook Introduction to Symplectic Topology written by McDuff and Salomon. So they have a collection of open problems there. You can see the problem number, but yeah, let's just see the statement. So when M is question 1, when M is a rational form manifold, we wonder if this symplectic morphism group is completely lying in the identity component of diff. Okay, so here we have a sub H in the sim here. That means homological trivial, because homological non-trivial maps are certainly not even smoothly isotopic to identity. So we want to kill that part. Okay, so basically this is asking what is sim H more smooth isotopy? Is this thing trivial? Okay, then the second question, originally asked by Arnold, like what is a symplectic mapping class group? Later, Donaldson wondered whether this group is fully generated by the Lagrangian dentist or square Lagrangian dentist. Okay. We also restrict ourselves to the rational form manifold for question 2. Okay. And for small rational form manifolds, by small I mean all the numbers small, or the blow up number small. This is studied by Gromov, Abreu, McDuff. I think I missed a lot long piece now. Sorry, and side elements. Okay. So question number 3, we are going to ask a similar question for the close relatives, which is a ruled form manifold, which is blow up of sphere bundles over genus J surfaces. Okay, whether this group trivial or not for any omega. Okay, those are the specific questions we are trying to address for today. So answers to question 1. This one, fortunately, we have a complete answer. That's joint work with TJ Li and Weiwei Wu. So statement is for any rational form manifold. For any omega, that's a positive answer for this question. Okay. Let me give a very sketch summary of the idea. Well, we are basically comparing this.
Sorry for interrupting. Again, that noise started.
Oh, sorry. Can you repeat the question?
Your noise again started, that background noise.
So I'm still having trouble hearing this question. Sorry.
Okay, now it's better. I mean, that noise that showed up again, but now it's better. Thank you.
Oh, thanks. Thanks. Okay. So we are basically trying to mimic the dimension 2 ideas, where the Bray groups arises as fundamental groups of the configuration space of points on S2. Okay, so here we are looking at the space of embedded balls. So here our M4 is a CP2. Okay, The basic idea is loops in this big space, this is infinite dimensional now, are going to be the elements of this homological trivial sims. That's not very precise, but the rough idea is this. Okay, and then we also have a sort of analog of the Artin generators, where we call ball swapping generators. So you can think in a break group case, we are swapping points. Now we are swapping balls. Okay, and then to attack this smooth isotopy question, the first thing we think about, or everybody could think about, is to isotope firstly an arbitrary loop in the pi1 configuration space to identity. That's actually pretty straightforward because here we have a CP2 which is simply connected, and then it's dimension 4. So like a configuration space is also simply connected. That means for any loop, we are able to at least homotopy it to the identity loop, which means a point. Okay, now I think standard modification will enhance this homotopy as a smooth isotopy. Okay, so here, I mean, we have some notation like a HST, which is the diffeomorphism of, which is a family of diffeomorphism in CP2. Okay, so here the T direction is a loop direction, and the S direction is the homotopy direction. Okay, we are able to do that at least. Now, the difficulty is try to extend this thing to the loop of balls. That means we have to preserve something in the radial direction, like the ball images. That's not for free. Okay, it's not for free. So somehow we have to find a trick so that the homotopy direction preserves ball images. Fortunately, for really small balls, there are some Lipschitz constant bound for any isotopy HST. If we restrict our ball sizes within that bound, we are able to have a ball image preserving direction. And then next we establish some trick to actually reduce the question to small size blowups. So that's basically the idea. Okay, I'll just say this much about this question 1.
Can I ask a question here?
Sure, sure.
Maybe just 2 questions. So for this M that you have, are you taking specifically like the symplectic form with, like you're taking the blow up symplectic form on CP2?
Oh, I see. That's a typo. That's a typo. So or bad notation. So here in the question, I'm using M. Downstairs, I'm still using M, but that M is supposed to be different. That's a blow down manifold.
Oh, I see. So that's
okay. Right. So here, my M is simply CP2 with the Fubini study form. Yes. Thanks for the correction.
And sorry, one more question. If I just give you the manifold CP2 connect sum with K CP2 bars, and I ask you like what symplectic forms are on that, are they all?
That's another good question I forgot to mention. So firstly, every form is a blow-up form. And we do have some reduction of the numerics of the form. Oh, actually, it's in the next page. Let me, let me move on to the question 2. Yeah. Okay. So, well, we mentioned in the beginning simplex sizes are important. So here are the possible sizes. Okay. To address question 2, we first have to understand what kind of cohomology classes can be there. So this is basically something like a simplex cone, but we are going to find some equivalence classes. Eventually, we are able to reduce everything to the so-called reduced simplex forms. And after normalization, meaning that we are requiring the original blow-up form, the original Fubini static form to have area 1 in the line class. Then we eventually land at k+1 dimensional polyhedron cone. That's a subset of the second cohomology of this blow-up manifold. So that's k+1 dimensional. Okay, then those are all the possible simplex sizes. I think that sort of answered Kevin's question, maybe not very detailed. Okay, great, thanks. Okay, then we are going to have some combinatorial structures in this pk+1. And in particular, we want to stratify this pk+1 by ADE Dinkin diagrams. Okay, so if you wonder where this ADE Dinkin diagrams come, they come from the intersection pattern of Lagrangian spheres. Oh, I think that noise is the fan of my computer. Okay, it's too hot. All right, so the forms are labeled by the, well, maybe I should mention more details. So here, let's take a simplex cohomology class. Okay, then we have a certain -2 spheres being Lagrangian. Then we look at their intersection pattern. So if the intersection pattern looks like a cut-down matrix of a Dinkin diagram, okay, the specific type of Dinkin diagram, then we say the omega class is of type A, D, or E. Unfortunately, we only have this like three types of Dinkin diagrams, nothing else, for at least for the rational for manifolds. Okay, a not very precise understanding is we are trying to look at the possible maximal plumbings of cotangent bundles of S2s in this rational form manifold, and then we define that as a ADE type of the simplex form. Okay. Anyway, after this understanding of the simplex cone or reduced simplex cone, we are able to address this question. So firstly, for type A forms, we also need another assumption. We want to have C1 NF simplex forms. Okay. In this case, the simplex American class group is trivial, or at least the homological part of the homological trivial part of that group is trivial. Okay, so here type A means almost all forms in this simplex cone, and then C1 omega greater than 0 means we are going to chop a small corner of the cone. Okay, that's a rough picture. And then for type D, this is one simplest of this pk+1. Given by explicit equations, like we want one bigger size blow up and then m smaller size of blow ups where m has to be greater or equal 4, and then we have even smaller sizes, but we don't care. So if we say such a pattern, then we are going to have m strand of pure braid groups of S2. So here we have a pure braid, which means a braid group mod some finite permutation group, because we are adding a sub H here. So on the left-hand side, we kill some finite homological action. On the right-hand side, we have to kill some finite permutation from the braid group. Okay, so here we also have the assumption C1 NF. Okay, that's the statement. Also, for those forms that we are able to compute the mapping class groups, we show that there is a parallel story, like a simplex Picard-Lefschetz theory, meaning that this mapping class group is generated by square Lagrangian dentist. Okay, so we sort of have some canonical generator. Okay, so very quick ideas for this second question. So this page is very sketchy, and I'm lying quite a bit here. Okay, so firstly, at least spiritually, there's a similar picture to the infinite dimensional moment maps where we make sim acting on the space of almost complex structures. Okay, so the details are the following. So firstly, we choose a filling divisor. I have a quote mark here, and I'll explain in the next page. Okay, but the upshot is we want the complement of this divisor to be simple, or at least something understandable. So we have R4 or puncture the R2s across R2. Okay. R4s are understood by Gromov, at least for the compactly supported symplectic momentum groups. And then just modifying Gromov's argument, we are able to understand the second guy, okay, puncture R2 cross R2. And then we are also going to look at the space of S. This is an infinite dimensional space. It is homotopy equivalent to some open stratum in the J omega, where J omega is a collection of compatible almost complex structures with omega. Okay, J omega has a simple topology, which is contractible. And the open stratum, at least we can understand part of its topology, the lower pi i's, okay, by some Alexander duality. Now we are going to look at such a transitive group action, okay, so that the orbit space is a J open, okay, at least the homotopy type is J open. It's partially understandable. And then the stabilizer is a stabilizer of the filling divisor. Now a quick illustration of what this filling divisor look like. We always try to make this divisor a comp-like divisor. So these lines are projective lines, meaning that topologically they are S2s. And then the stabilizer are going to look like a purebred group of M strands, where these M strands are the intersection points on this horizontal S2. Okay, that's a rough idea for question 2. I mean, then the next is to play with the symplectic sizes. Whenever we see a equal size like this, we are going to prove that these as rate generators in the step S are going to survive in the pi 0 of sim H. Otherwise, if we have distinct sizes, like for type A, we have a lot of distinct sizes, we are going to prove that the ball swapping map for different size balls are not going to survive in the pi 0 of sim H. Okay, so that's a very sketchy idea for the second question. It's worth remark that this is some parallel story to two-dimensional topology or geometric group theory. So the first idea is a symplectic momentum group of a 2D surface is homotopy equivalent to the orbit of a filling system of curves. So here, curves, we really mean like S1s or simple closed loops. So what is a filling system of curves? Actually, there are some topologies or dynamicists, I think about this kind of filling systems. So if we have a collection of A's, a collection of B's, they are simple closed loops in the surface. We call it a filling system if they have a minimal intersection. That means a geometric intersection equal the algebraic intersection, like pairing in the homology. Okay, then the complement looks like a union of disks and the ones puncture disks. Well, if you think about that, this is quite similar to the requirement we have here for the complement. Okay, then previously, similar object actually appear in the study of symplectic geometry. We have a Biran decomposition. That's not very similar, but at least share the same inspiration, I think, from dimension 2. So Biran takes a isotropic skeleton and then prove that I think this is quite general. We can always find such thing so that the complement looks like a disk bundle over a symplectic Donaldson hypersurface. Okay, and then Joe Coffey actually tried to recover the topology of 4-dimensional sim from the space of isotropic skeletons. Well, sort of have the similar idea as we have here. Okay, but I think we are the first to make this filling divisor explicit in the 4-dimensional rational manifolds case. Okay. All right. Question 3, let's change gear. I'll say less about this question because we already ran like 40 minutes. Okay, so that's a joint work with Olga Buse. Basically, we are able to find forms on non-minimal ruled surfaces so that we have the non-trivial symplectic mapping classes. Okay, but it's unfortunate that we don't have explicit computation for the full mapping class group, but we conjecture the mapping class groups are brace. Maybe this is a too vague statement. Let me talk about some idea and maybe give some insight of the picture. Okay, so firstly, we take a blow up of sigma j cross S2. And then we are not going to directly study the mapping classes on that manifold. Instead, we are going to change our symplectic form in such a family. So our family actually stretches the base or the sigma j factor. Okay, I mean, we start with a omega 1, okay, where we have a split symplectic form of the blow down, and then we correct the form by blow ups. Okay, and then oops. Oh. All right. So now we are going to stretch this form on the sigma j and look at the limit. So now the ruled surface actually looks like a very large symplectic sigma j, okay, with a bunch of punctures. We can think the blow up balls are punctures in the sigma j. Okay, using some stability argument, that's by some inflation technique created by Lalong and McDuff, we are able to prove this process preserves the mapping class group. Oh, that should be diff 0. Okay, that should be diff 0. Oh, sorry. I think the connection is not stable. It's probably okay now, right? So we are able to prove that this like a limiting process at least preserve the pi zero. Okay, provided that we start with a root surface with a large base. Okay, then we are going to look at the limit. So here, to study the limit, we actually think about again a group action where the total group is diff 0. And then we try to act this big group on the space of singular foliations that's isotopic to the standard one. So let me give a quick picture of the singular foliation. So here, if we take the blow down, there's a standard product foliation, like foliating this root surface by P1s, okay, where we have a sigma G as a base. Then if we blow that up, we are going to have something like this, singular fibers, where a sphere breaks into 2 spheres or more spheres. Okay, then the key point is if our symplectic form we choose here has all the equal size blowups, then we don't have such bad breaks of a single sphere. You know, or equivalently, we only have such singular fibers that one sphere breaks into 2 components. Okay, we do have some control here. And that's why we claim there exist some simpler forms. That's our choice of simpler sizes. Okay, so now the rough idea is we look at the loops of the foliation space. There are some swapping of the singular fibers. And then if the blow-up sizes are small, we are able to prove that such loops are going to contribute to non-trivial pi zeros in the fiber group, which is the limit of the symplectic mono group. And then because our step 1, the inflation process preserves the pi zero, then we are able to show that there exist non-trivial symplectic mapping classes for at least this symplectic forms. Okay, so that's a rough idea. All right, so those are the results that I plan to talk about. Now we have a bunch of questions. Most of them are open and some of them are hard. Okay, so the first question, we apparently have 2 approaches for the different kind of mapping class group problems. For question 1, question 2, we are basically using the ball packing approach. And then for the root surface, we are basically using the foliation approach. It seems like those approaches share something in common. And we wonder if we are able to interchange the approaches for different questions. Okay, so for the first direction, if we are trying to apply the foliation approaches to, for example, question 2, which means rational surfaces, that's sort of straightforward. I actually believe there is such at least a reproof using foliations. Because if we throw the CP2 and the host group surfaces away, we basically have blowups of S2 cross S2. The same foliation actually appear there. But the problem is in the rational case, because the base and fibers are both genus 0, the degeneration, have some interactions. So that's actually some extra difficulty there. Maybe it's not worth spending that time, rewriting the proof. Okay, but this other direction does have something worth thinking of. Well, at least in my own opinion. Okay, so here are some questions about using ball packing approach to address question 3. So the first question, which I believe have a positive answer, but we haven't really write anything down yet, is that looks like the switching singular fiber maps or the loops are quite similar to the ball swapping loops. Well, we wonder, is there a direct equivalence or at least some isotopy between those two kind of maps? Okay, so a more general question about this is about the topology of ball embedding spaces. So basically, we are still trying to compare the space of balls with space of points, which means the configuration in spaces. And then there are some forgetful maps, like sending the ball to their centers. We wonder how much the similarity between the two spaces, and that's a conjecture made by Weiwei and myself. We are wondering if we have a nice control of the simplex sizes, small ball sizes, then certain level of homotopy groups of the configuration space should be pulled back to the space of embedding of balls. Okay, in particular, we conjecture when the sizes are small, we have some levels of vanishing of homotopy groups. Okay, I mean, let me quick note that we only know the -1 kinetics. Here I'm asking the M kinetics. -1 kinetics means non-empty. That's actually double theorem. I mean, when we control the ball sizes very small, we are always able to embed it into the double chart. Now the next level, even the 0 kinetics, which means the kinetics of embedded balls, are still open. For almost everything that's not a 4-dimensional rational ruled manifold. Okay, so this conjecture in full generality is too ambitious, but probably for ruled surface, there are something to say. Okay, so that's the first thing we want to ask. And the second thing is actually, we try to relate this swapping fiber map to the fiber down twist map. Okay, again, there's nothing written down, and some initial ideas are like this. So let's recall the fiber down twist. So we want a domain with circle fiber contact boundaries, and then we have a boundary contact morphism that preserves the circles like set-wise, fiber-wise. Okay, then we try to extend such boundary maps to the domain. Then that kind of map is a fiber down twist. That's originally written in the Biran Girou's talk. I think they never published a paper. Okay, so here is what we propose to attack such a problem. So let's remember we have a sigma g, and then we have a certain singular fibers, and then the maps are given by swapping singular fibers, maybe something like this. That's a loop of foliation. Okay, so now if we restrict ourselves to a domain like this, that's close to one of the section. Okay, then on the boundary, I believe we are able to achieve a contact type boundary where the boundary intersect all the leaves. Those are the P1s transversely, so that on the boundaries, those are circles, S1s. So now if we take a loop of this foliation, at time 1, everything goes back to itself. That induces a map on the boundary that preserves the circle. And then we are able to, actually, it's not we are able, it's natural that this swapping fiber map extends this boundary circle maps to the red region. We do have a domain map, but the problem is fiber dentist is supposed to be a compactly supported map. So here our construction, like a swapping fibers, sort of have a global nature. So we wonder if we are able to isotope, this map to make it supported near some of the sigma J's. So, well, last time I thought about this is like half a year ago, so I don't have any new idea. Maybe I'm missing something that could be a simple remark to add there. Okay, that's question number 2. I mean, it's also worth noting that in this ruled surface, blow up or ruled surface, there are no Lagrangian spheres. That means the non-trivial mapping classes are certainly not Lagrangian dentists. So then the next natural candidate to think about as a non-trivial generator of the mapping class group are the fiber dentists. Okay, so that's the second question. Those are, I think, approachable questions. Now, some questions may be out of reach. So we have some Nielsen-Thurston theory in dimension 2, where we classify the surface mappings into 3 kind of maps according to their different behavior, different dynamical behavior. Okay, we have a periodic, we have reducible, and we have a pseudo-anosoph. So pseudo-anosoph is a generic case, like you randomly pick up a map, then probability 1 it is a pseudo-anosoph, and then there are some ergodic property which makes the map really important here. So theorem is saying that those maps can be classified using the following dynamical properties. Like here, the iota alpha Fn alpha means the geometric intersection between the original simple closed curve with the nth iteration of this curve using f. Okay, so now the growth rate behave completely different for the 3 kind of maps. So for the periodic ones, we have periodic intersection numbers. Okay, that means after some iteration, the map, the alpha becomes itself. Okay, all right. So now for the reducible ones, the growth rate is sublinear, and then pseudo-anosoph, we have exponential growth rate. At the same time, this geometric intersection can be interpreted as rank of the Lagrangian intersection flaw homology in dimension 2, right? Also, in higher dimension, we could think about something like this. Okay, so now let's take the answer to question 2, where we have a rational form manifold. We have a break group for some of the simple forms, and we have some natural generators, which are dentist along Lagrangian spheres. So abstractly, in a break group, we can write some word. Then I am able to tell, or at least able to ask a computer to tell whether it's pseudo-anosoph or not in dimension 2. Okay, so now we can write the same word for the 4-dimensional mapping using the Lagrangian dentist generators. So we do have some 4-dimensional candidates. And then the natural question is to ask whether that map, 4-dimensional map, is still anosoph in this sense, like the growth rate of the Lagrangian intersection are exponential exponentially growing. This could be hard, but there are some related results, pretty interesting. So firstly, we may not attempt that ambitious problem in the first, not asking for any Lagrangian. Let's say a simple Lagrangian, like a Lagrangian T2. Okay, we do have a reason, because another interpretation of the pseudo-Anosov map is that it preserves the foliation. Okay, in higher dimensions, that's supposed to be a Lagrangian foliation. Then that gives us some restriction of the fiber topological type. That has to be a Lagrangian torus. Okay, then how about we pick up some simple T2s in the rational form manifold and then ask what's the growth rate of such sequence? Okay, so Biran into topology has a result, but that's for Hamiltonian. Okay, saying that the generic Hamiltonian on a CPN, when iterated on a Clifford torus, the growth rate is at least 2 to the power n. So this kind of result, we do have that before. Okay, so now I'm trying to ask this question for non-Hamiltonian map. That's question number 3. So question number 4, maybe even more outreach. That's like asking for other type of simple form manifolds. I actually think I'm over time, so I will actually stop here and leave this one to the informal discussions.